nucleophile. If you have a nucleophile, you cannot make an electrophilic aromatic substitution reaction, right? You probably know that. This must be nucleophilic aromatic substitution reaction. And then the good thing is this benzene electron density can be drawn by having electron withdrawing groups like a nitro and two chlorine there. And we're really talking about that this nucleophile is not going to replace the nitro, right? Because nitro is not a good leaving. It's going to be attacked either of this chlorine. It's going to replace either of this chlorine. The question is, which one? It's going to replace the one, the meta to the nitro. It's going to replace the one, the para to the nitro. That's the question. When you are in doubt, what you need to do, you need to draw the mechanism. The mechanism is basically looking at the intermediate produced, and the more stable intermediates will lead to the major problem. So that's why the mechanism is something that you're going to use when you don't know what to do. So let's look at both cases one by one. First of all, let's look at this chlorine at the meta positions. You got the nucleophile makes an attack here. That produces negative charges here, right? That is going to make the resonance structures that goes here, that pops out. There's another sigma complex. And then that can go in and then make negative charge go out. And that's kind of good because of chlorine, and it's a related to withdrawing group. So if the carbon burn the chlorine, negatively charged is better compared to other ones. So, but this is the only resonance structure we can draw by having this one attack there. Let's look at the other one. If this one attack the chlorine at the para positions, so let's look at what resonance structure does it mean. One, it makes the attack there. So we got the methoxy substituted at that positions. Negative charges goes here, that position. It makes the resonance structure the same way. It comes in, it pops out right here. This one, I think, is a good one because not only this, you can have a nitro groups pull out electron density out of the ring. It can make another resonance structures. This one, you cannot make any of these because negative charges never appears on the carbon bearing the nitro, right? This one still goes in, one of the resonance structures, this one comes in that pops out there. That is kind of equivalent to that one. You got the carbon bearing the chlorine, negatively charged, so it's kind of a better than others. But this is the one that makes a big differences between these two. This is one only available by this one attacking by that carbon, not this one. So which one of these two groups of resonance structures are more stable? Then you should choose this one, and that one is going to lead to a major product. I'm not saying that this will never form. This may be formed by a very small amount. This one will be formed as a major because we have a much more stable resonance structures. So the major product from this reaction, this one, the para, chlorine, the para position replaced by the nucleophile, that is going to be major products, not that one. See, the mechanism is important. You cannot simply just memorize these things, unfortunately. This is something you really have to work it out. So I hope that you understand why there are equally substituted. The one in the para position to nitro, that's the one that goes better. Because it makes a more stable resonance structures. Okay, have enough? You look like one. Another one. But this is going to be critical because the thing is, this conceptual question can be easily hooked up to a ranking question. In the case of ranking, the type of things we could normally ask, order of the reactions that goes past a particular mechanisms or things like that. So nucleophilic aromatic substitution reaction or electrophilic aromatic substitution reaction, we can give a bunch of molecules and we can ask you to rank them. And then you need to figure out what to do. I mean, electrophilic aromatic substitution reaction, people is actually more easier there to understand that somehow. The nucleophilic aromatic substitution reaction, people has a little trouble. That's why I'm hitting these questions over and over again. So you understand the differences between these two. All right. question is this. There are two molecules going through the nucleophilic aromatic substitution reactions. Which one will be faster? That's the question. Which one will make a faster nucleophilic aromatic substitution reactions? Well, this was a pretty easy one at least. And as I said, nucleophilic aromatic substitution reaction, you want to have the benzene ring electron density withdrawn by having electron withdrawing groups. This one has a 2, that one has only 1. So supposedly this one will be better. But let's show how that additional substituents can help out stabilizing simpler complexes. Let's look at the simpler one first. The toxic groups is a nucleophile. It makes an attack to the carbon bearing chlorine. So you get the aromaticity broken here by having a negatively charged shows up there. That's the same thing we've been doing. That sigma complex is going to go around. It's going to go pops in. That comes out. That carbon bearing nitro. That's the one that makes an additional resonance structure with the nitro groups, which is good, right? So that's why the nucleophilic aromatic substitution reaction can happen here. But this one can also pop out there. There's another resonance structures. So these are all the resonance structures you can draw from this molecule. It's already a lot. So that means it can happen. I'm not saying that it won't. It can happen. That can also happen there too. What I'm asking is which one will make it faster reaction? That's the thing. What will make it faster? So let's look at this one. It's going to make the same position attack. This carbon bearing the chlorine get attacked by the nucleophile. We get the 2 substituted there, aromatic is broken. You get a negative charge, it shows up right there. That's going to go around the ring the same way. It goes up to that position. That's exactly the same as that one, right? Or this one. Nitro group is participating in making resonance structures. This was equivalent to that one, right? And this one comes another resonance structures. Another negative charge shows here. Which is equivalent to this one, but that one has no substituents. That one has a carbonyl there. Carbonyl can make up another resonance structure, right? It will make up one more. But this one more, but that means that oxygens are going to be negatively charged. Out of so many elements, oxygen can handle negative charges way better than others. So this is a pretty stabilizing one too. So it's just one more, but that one more resonance structures can make a differences, especially if that's more stabilizing one. I mean, this one's good, but that's also there too. So this one make the most stable resonance structure. Sigma complex are more stable because of that. That's the reason I think, this will be substituted by the methoxy groups that produce this, but this reaction will go better, making this one faster because it's the more stabilizing intermediate. And you've got to draw a lot of resonance structures. So all the practice we have done this semester is going to shine. I really hope that with your practice drawing these resonance structures, you're going to do a lot. This was a simple one compared to the next one. This one is what I really like. If I ever going to make the question harder, I will ask this question, not the formal. This type of same concept. There are 2 molecules with a nucleophile. So this is the nucleophilic aromatic substitution reactions. But which one will go through the reaction faster? Previous one has a 2 electron withdrawing groups, the other has just 1. So the one with the 2 electron withdrawing groups makes it better. On the other hand, these two nitro. Same number of electron withdrawing groups. Only difference is where they are. There are these 2 positions here, there are those 2 positions there. So number of electron withdrawing groups are the same, nitro groups are the same, but positions are different. Would they matter for the nucleophilic aromatic substitution reactions? I mean, both will be substituted, I guarantee. Both will be substituted. We have done this before. But one goes faster than the other. So which one will be faster? if you remember what I said already, I already give the clue. If you look at the mechanism of the nucleophilic substitution reaction, where the negative charge typically shows up, ortho and the para position. So if you want to stabilize that, you want to have electron joint groups, ortho and para positions, right? Not the meta positions. That's the clue. But of course, I'm going to show you. So let's look at the sigma complex. That's the only way to explain this thoroughly. So let's look at that one first. Nucleophile is going to make an attack to this carbon bearing the chlorine, all because it has a leading group. You cannot replace the nitro groups without. So there's no way this will be substituting there. So this is a carbon attacked by the nucleophile, which is an aldoxy group there. And then aromatically broken like this. So this carbon is going to be negatively charged right there. All the position. That will make a resonance structures. That comes in, you're going to get negative charge right here. And of course, negative charges carbon next to the nitro groups is a really good. That makes a more stabilizing sigma complex. That is good. But this is not the only one. Now this negative charge can appear as ortho position there. So you see here, ortho goes a para, then goes ortho, right? So if you want to have electron withdrawing groups, you better have it on the ortho or the para position. Para position, yes, you do have a nitro groups there. But that position, you don't have that. You got nitro groups at the meta position. This carbon, negative charge never show up in the sigma complex. That can help by the electron withdrawing electron density through the bonds. That's inductive effect, but not directly participating in and making additional resonance structure. That is not working that way. So this is all the resonance structures we can draw from that one. And then let's say we do this one here. It makes an attack there. It makes that one negatively charged, which is the exactly same one as we draw that one. It can go over that position the same way. You can have a negative charge next to nitro groups. Yes, that's good, just like this one does. It makes another resonance structures like that, like this one. So up to here, it's almost equivalent, right? But it will pop up another resonance structures to the ortho position there. And here, now we have a nitro groups right here. That's the differences. Nitro groups there or there. That makes a difference. Because that's the carbon ortho position having a negative charge. You want to have electron withdrawing groups there to make the reaction go faster. It will stabilize it more. The nitro groups make another resonance structures. So that's why electron withdrawing groups, ortho, these two positions and the para position is good. The one in the middle is not directly helping. It helps indirectly by through the inductive effect. So that's why you can make a lot more resonance structure, one more resonance structures if you got the electron withdrawing groups ortho para position, not the meta para position. Right? I really hope that you see the differences between these two. So both will make a substituted product. This group is substituted with the toxic groups, that will be substituted with the toxic groups, but this one will go faster because it has more stable sigma complex can be made.